But it is basically, we're also going to do a little Desmos activity tomorrow, so make sure you bring your computer. And then we'll get to work on the project, and I'll give you the rest of the class to work after the, although I thought about doing the Desmos today.
No, I think we should work on the packet.
Okay. And do the other tomorrow. All right, so stretches and shrinks can get kind of sticky. Your red sheet is going to be your friend, okay? So we talked briefly yesterday about stretches and shrinks of verticals and horizontals, but I want to go into just a little bit more detail and then talk about how we're going to apply it. So, I would probably put it in the notes, and then we'll move into the packet, the work packet. All right, so I'm on the bottom two rows of your red sheet here, and those are the two that we're focusing on today, and we're also putting them all together. And I feel like I threw a little something, yeah. We'll talk about that. So we're going to talk about stretches and shrinks, and then we're going to talk about the combination of all of them all together. All right, so the last two, we have a times f of x, and we have f of a times x. So this is kind of the difference yesterday where we were talking about if the plus or minus is hooked to the x, or if it's just thrown outside the equation there, what it impacts and what it affects. So if the number is just outside, in other words, if I just have 3x squared, okay, that's what I'm talking about. For example, 3x squared as opposed to 3x squared. You see the difference? One's hooked just to the x and one's just thrown in front of the equation there. So inside the parentheses or not. If it's just in front, that's when it's a vertical stretch or shrink, depending on if my a is bigger than 1 or less than 1. So if you look on your sheet, it says if the absolute value of a is greater than 1, it's a stretch. And if the absolute value of a is less than 1, then it's a shrink. And we're talking about vertically. So this is where I got my little spaghetti noodle or my elastic y-axis that I'm stretching out or I'm shrinking in, okay? So in this case, the bigger that a gets, the more stretched out my vertical axis is, okay? And one thing that's not on here that you'll probably want to add is your stretch or shrink factor. And that is A. Okay, so in this case, if I was asked to describe the transformation here, this would be a vertical, it's bigger than 1, so it's a vertical stretch of 3. Does that make sense? Now, if you look at your little XY, and we're just going to camp here for just a minute, and I'm just going to use this exact same example here. If I use 3x squared, and I'm asked to graph that, okay? You look over in that last column, that change column, it says that xy becomes x a times y if it's a vertical stretch or shrink. So what that means is I've got my parent graph. And again, you don't have to draw the parent graph every single time. But I'm going to draw it just to help you see. There's my parent. Now if I want to graph 3x squared from my parent, so this says take every point that was on my parent graph. 0, 0, 1, 1, negative 1, 1. And to find the new point, I keep the x the same, but I take every y value and I multiply it by a. What is a? 3. So 0, 0 becomes still 0, 0, right? Because 3 times 0 is 0. 1, 1 is going to become, the 1 stays the same, but then I have to do 1 times 3, which is 3. So this new point is going to become 1, 3. This point, the x stays the same, but I multiply the y by a, so it becomes negative 1, 3. So the red one or the pink one in the middle there is my new transformed graph. Does that make sense? Does that look like a vertical stretch to you? Yes, because if you took that y-axis and you stretched it out, that's what it would look like. Does that make sense? Let me give you another vertical to try and see what happens. So we said vertical. Sorry. And I'm going to put the parent, again, you don't have to do the parent every time, but it may be helpful for you as we start. To see if you can find the new graph there. Is it a vertical stretch or shrink? Shrink this time, right? This is a vertical shrink. And so I look at the situation that I'm in here, and it says that I take every point and it becomes, I'm in the same situation, x a times y. So this one would be a vertical shrink of 1/2, right? So my old points, remember, were 0, 0, and I'm going to do this a little bit different this time to see, maybe this helps you see it a little better. These are my parent graph points, and they're going to become 0, 0. 1, what does the y become? 1/2, and negative 1, 1/2. So 0, 0, 1, 1/2, negative 1, 1/2. Does that look like a vertical shrink? Looks like you smushed it down and it's coming out the sides, right? Does that make sense to everybody? The verticals are easy. The horizontals get a little bit harder. I got that? All right, let's talk about horizontal. Remember, everything with x always ends up being the opposite of what you think it would be. When I subtract, that really means I'm moving right instead of left. Same with shrinks and stretches. So if you look, this is when I'm in the boat of a times So, for example, let's do an absolute value. F of x equals, now for this one, everything is backwards. So if the absolute value of A is less than 1, what does it say happens then? It's a horizontal what? Stretch. And if the absolute value of A is greater than 1, it's a horizontal shrink. Okay. Now we talked a little bit yesterday about how a horizontal shrink is the same thing as a vertical stretch, and that's why. Okay, so they kind of do the same thing there. But because this is in parentheses, I'm going to treat this as a horizontal shrink or stretch. Shrink. Of, and now I got to think about my factor. In this case, the factor is 1 over A. So you got to flip it over, because I wouldn't say it's a shrink of 2. That doesn't make sense. I would say it's a horizontal shrink of 1/2. So you take this A and you flip it, and that's your factor, your shrink or stretch factor. Right. Now, this one says, take your points and they become x over A and y. So this time I'm dividing instead of multiplying. This is where they get a little bit harder. So let's see if we can graph this absolute value of 2x and if it looks like a horizontal shrink like we said. So if it's a horizontal shrink, should my graph get skinnier or wider? Skinnier, that's right. If I squeeze in those horizontally, it should get skinnier. So let's see if that happens. I'm going to plot my, again, you don't have to do this. Let me go back. I'm going to do my parent graph here. And we said we are doing f of x equals the absolute value of 2x. So all of my points are going to become x over a, bless you, but y is going to stay the same. So my points on my parent that I'm using, 0, 0, 1, 1, negative 1, 1. Are we all in agreement? Okay. So each one of these, what is my A? A is 2. The factor is 1/2. Okay. So here this becomes, well, 0 divided by 2 is 0. So I'm still at 0, 0 for my vertex. As long as I'm not doing any shifts. When I start moving left, right, or up and down, it won't still be 0, 0. But yes, if all I'm doing is a dilation, then yes. What does 1, 1 become? 1/2, and the y stays the same. So negative 1, 1 becomes, that's right. So let's plot these and see what they look like. I got 0, 0, 1/2, 1, and negative 1/2, 1. Does that look like a horizontal shrink? Yes. But it also looks like a what? A vertical stretch. That's exactly right. Because a vertical stretch is the same thing as a horizontal shrink, and a vertical shrink is the same thing as a horizontal stretch. All right, so graphing them is not too bad. Writing the equations of them proves to be a little bit more difficult. So let's look at that. I'm looking at number 23 on your packet under stretches and shrinks. And I am going to copy this graph on here while y'all get that out and try to find that packet. I think I accidentally printed two whenever I printed Aiden's. I think there's one on the printer. By tomorrow. Yeah. Well, tomorrow by class. It's like homework tonight. Yeah. But you already did half of it, Aiden, right? You should have. I forgot to take questions about your homework. Okay. I did ask how it was. Everybody said it was easy, but then I forgot to say to him. So you just do that. All right, this is 23. No, that's the only one. Did you break it, Aiden? Oh, there's some staples on my desk. Look at that little turnabout thing on my desk. This is 23. Some smart aleck broke them all apart, so they're not big whole long pieces, but there's no telling. All right, parent function. What's the parent here? You all know this. Yes, the absolute value. Now it asks me for the transformations done. What does this look like to you has happened? What kind of stretch? A vertical stretch. Somebody said a horizontal something, and I would say, oops, you're not wrong, vertical stretch. Or you could say a horizontal shrink. Okay, either of those would be okay, but you're going to have to make sure you get your factor right if you do that. Okay, so let's look at the vertical stretch first. If you're not, you probably can only put like one broken piece in there. You can't like, you know what I'm talking about? So let's go with vertical stretch first. The way I do these is I'll find the closest exact points on the graph that I can find. In other words, I'm going to look really close here and see where it exactly crosses over somewhere and the closest I can to the origin. So it looks like the first time it crosses over an exact point is at 1, 5. Would you agree or disagree? Agree. So if I think about the parent function, and I'm going from -1, 1 to this, would it be easier to describe this as a vertical or a horizontal change? Vertical, why? Because the y is the one changing. It's easy to identify that, right? So on my paper, I'm probably going to go with vertical stretch and not worry about this part. And I'm going to call it a vertical stretch. Now, here's where you really have to think. If I went from this point, went from 1, 1 to 1, 5. You need one of those two numbers to stay the same, okay, so you can identify your factor. If it went from 1, 1 to 1, 5, what was the stretch factor? 5. That's exactly right. So I got a vertical stretch of 5. Once you've identified this, it's easy from there, okay? You want the equation. So if you're doing a vertical stretch of 5, what does your equation look like? Does vertical go outside or inside? Outside. 5. Horizontal goes inside, vertical. See why these are a little harder than just the slides? They get bleh. What's the vertex of my absolute value now? 0, 0. That's exactly right. My vertex has not changed. How about the domain? What is it? The range, though, 0 to infinity. Okay? So when you're identifying this, you're going to try to identify the stretch or shrink factor. You're going to find a point that either has an x value of 1 or a y value of 1 so that you can find out what's being done to stretch it or shrink it. Does that make sense? So like on number 24, look at 24. I would probably pick, it looks like 1, 2, 3, 1. Do you see that? So 24 has the point 3, 1 on it. I want one of these two to be 1 because I know I'm going from 1, 1 to something. And I don't want to have to multiply both of them. I just want to have to multiply 1 or divide just 1. So for this one, I would pick 3, 1. Well, how did I get here? What did I have to do? My A would be 3. And that would be, actually my A would not be 3. What would my A be? To get from here to here, I multiplied by 3, right? But remember, this one is horizontal because it's impacting X. So what would it be? Remember, you're doing the opposite. What would your A be? 1/3. Horizontal flips. Remember? So my equation for this one would be inside, but it would be 1/3 X. Yes, because it's horizontal. Let me do that so you can see it all. Because look at your red sheet. When you're horizontal, you're dividing X by the A. So this would be a horizontal shrink, yes. No, stretch, horizontal stretch. Horizontal stretch. It's a horizontal stretch of 3. Your A is 1/3 though. Because your stretch or shrink factor is always the flip of this. Remember, look at your sheet. If you're horizontal and your A is less than 1, then you're a stretch. So this is a horizontal stretch. These take some practice. Absolute value. We didn't do them all. I was just showing you how to pick the difference. Yeah. Flip over to where number 37 is. There's a little box above. It says combinations of transformations. Y'all need a break in between? Y'all want to take a little brain break? Okay. Combinations of transformations. So it gets kind of hard when you start thinking about what you need to do first. I probably should have.
Wait, where is this?
Number 37. Oh my goodness, I put that in the wrong place. That should actually come before number 40.
Which 37?
The one with the little blurb above it. Okay. So, the one that says above it says combinations of transformations. Y'all so nice to each other. 1, 2, 3, -6. Can y'all see those little lines? Because I have a little bit of trouble with it. This to me looks like where that one's crossing. Tell me if you agree or disagree. That looks like the first exact point that I can pick. I got -3, -6, and then this would be -2, -4. Looks like on it. Does that look right to y'all? Okay, so let's talk about how in the world are we going to write the equation, because we know on a normal parent graph from 0, 0, I just go up 1 over 1 to find the next one, right? But this one's going up 2 and over 1. So how in the world are we going to figure out what transformations are being done? So the first thing I want to look for is I'm going to identify that vertex, okay? I'm going to find that vertex and I'm going to say, where has it slid? So tell me how the vertex has slid. Left 3, down 6. Do you agree or disagree? All right, so first step, we're going to find the vertex. And we're going to talk about how it slid, okay? The next thing that we want to do, does it have a reflection? This one's a no. After we've identified a slide based on the vertex, and if it has a reflection, then what we're going to do is we're going to try to identify the shrink or stretch, okay? And to do that, we're going to pretend like this is the easiest way for me to see. This point, if I slip this back up to the origin where the parent goes, right, I would be at 0, 0, over 1, up 2, over 1, up 2. So this is 1, 2. So the point 1, 1 became 1, 2. What type of stretch or shrink is that? Vertical what? Stretch. It looks like a vertical stretch of what? 2. Remember, vertical is what it is, horizontal is opposite. Okay, so it looks like a vertical stretch of 2. Does everybody see how I got that, how I kind of reasoned through that? Find your slides first. Identify your vertex and find your slide. left, right, up, down. Then slide it back to the origin so you can see, well, how did it move? So if it was right here, this point is from the vertex is up 2 over 1. So if I were up here on my parent function, it would be up 2 over 1, and that's where I would be. The vertical stretch of 2. Well, I wouldn't necessarily graph the parent. Like, I would look, the first thing I do is look at my vertex, right, and see where it slid. Now, if you took that pink one and you slid it back to the origin, so in other words, if I moved it back up here, this point would land at 1, 2. You see what I'm saying? Because I need to find that factor. I need to find how it changed. So I'll usually just count and say, well, this point is up however many and over however many from the vertex. Now what I want to do is write my equation, because that's all I got, right? Slides, left, right, up, down, reflections, and shrinks or stretches. So if I want to write this, what do you think this equation looks like? What's the parent graph? X squared, right? All right, so that would account for my stretches and shrinks, but that doesn't account for my shifts. So it goes, because this is vertical, it goes in front of the entire equation. So 2 times left 3 would be plus 3, and down 6 would be minus 6. This is hard. Yes. It is. Yep. Yes. The test, I don't know about the test. We'll see.
Just like let's get a little cheat sheet, like you can write down. Yeah. But like a little bit bigger than this.
We'll see how y'all do with this first. We still got a little while.
It's just because like
Yeah.
it's just a lot of.
If it's down, it's a reflection. Skip that. Number 38 is a reflection. Do you want me to? All right, 38. Oh, yeah, what's the domain? What's the range? This one? We've done it so much. Unless it's an open circle. Like, if it was like that, that would be a parenthesis. None of these will have circles. Like if it's, yes, yeah.
So they're all gonna be brackets?
For these, yes.
Wait, like for this entire packet, they're all gonna be brackets?
On the numbers, yes. Yeah. So we started with, what did we start with in this unit? We started with parent functions then. Oh, piecewise. So it's, no, was that on the last one or was that on this one? Yeah, step function, absolute value, piecewise, and then function transformations will be on the next test. This is the last thing that'll be on this test. Yeah, next week. I'm probably next Wednesday, maybe next Thursday. Yeah. And I'm thinking I'm going to give you your project tomorrow, and won't be due until probably next Friday. Be a week to do. It's one of the picture projects. All right, let's do 38. All right, guys with good eyes. What's it look like my vertex is here? -1, -3. What's the next closest point there? 0, -4. All right, so parent function is obviously what? Parent function. Quadratic, which is x squared. That's exactly right. So this would be x squared. So now let's identify the transformations. How about left, right? Anything? Left 1 and down 3. Does that make sense to everybody? This is my parent. How did I get here? Well, I went left 1, down 3. Okay. Do I have any reflections? Yes, this one does reflect. Does it reflect over X or over Y? X. Do I have any shrinks or stretches? I hear no and yes. If I flip this one back up and I slid it back up here, the next point is 1 and 1 away. 1 and 1 away. So no, I don't have any shrinks or stretches here, right? Do you see that? If you have to go up 1 over 1 or down 1 over 1, it's just 1 to 1. You don't have any shrinks or stretches. You don't have to worry about them. So now I just have to write this equation. And maybe it'll be easier. I don't want this to confuse you, but it might help you. Vertical shrink or stretch. Somebody grab the left, right. Mm-hmm. Up, down. If there's no vertical shrink or stretch, if none, 1. It would if it's a reflection, yes. So because this is reflected, I'm going to have to put a negative in front of the whole thing. And then it moves left 1, but remember it's to do with the x, so it's opposite. So left is going to be plus squared, and then down 3. It's not as bad when there's not a stretch or a shrink in there. It's a lot easier. Bless you. So it had a vertical stretch of 2. I took those points to get from the vertex to the closest point. I had to go up 2 and over 1. So if you go up 2 and over 1, that means you multiplied y by 2. How about the domain here? What about the range? Close. Negative infinity to -3. This one opens down, so you got to go from the lowest up to the highest. So negative infinity up to me. When you get over to number 40, that should be a little bit easier for you. You'll identify the transformations. The question is, what do you do and in what order? When you do these, okay, you will Go in the order of operations as you apply. So I'm going to do my, let me just write this out. This is what I have printed up here. Yeah. Welcome. I'll give you a second before I keep talking. That's correct. That's correct. All right, so as you go through the multiple transformations on 40 through the end, my advice to you is do any reflection first. Go ahead and flip it if it's got a reflection. That'll make it easier for you. Then do your stretches or shrinks, and then do your shifts. Does that make sense? All right. That's all I got for you. I'm going to let you work together. I know you don't have a whole long time.